what the mean of vibration? What the vibration mean? Vibration is repeated movement or action happen due to external force. Especially if we talk about the machines like this, we found that if you take measure or you measure vibration on this engine, if it's not working, it will not make any vibration. But once it starts working, it generates vibration. Then the vibration here is the response of the force. Then the response here count in two parts: for the external force which acting on the body and the response of this object or this body. And depend on the force and the response, you found the amount of vibration. Like if I'm pushing a small object, it will move easily, but if I'm push big object or big mass, you found it's not moving the same way. Then why we measure vibration? Simply to provide this kind of failures, these catastrophic failures. Because in early stage, when you detect the failure, you don't know exactly what the time between starting the failure and the complete failure. Sometimes it's run, I mean the period between detecting the failure and the failure itself is not too much. Then you need to take action as fast as you can. The same here, like these kind of failures, it's very catastrophic failure. What types of failures we can detect using vibration analysis? What problems we can detect it? We can detect many things, like motor faults, which here we talk about electrical actually, eccentric rotors, mechanical looseness, bearing wear, rotor rubs, soft foot, lubrication issues, unbalance, misalignment, and more. Not only this, but there is many things or many faults we can detect using vibration analysis with different techniques, with different ways. Like here, simply by talk about vibration, we found we have three types of vibration. First, we call it free vibration. What the mean of free vibration? Free vibration, that mean it's like this mass spring system. If you pull this mass and let it vibrate, you found it moves up and down, making this curve here. This waveform is due to free vibration. We found this value here or amplitude here is high and start to go down a little bit until it's go to rest. In this case, because it's free vibration, there is nothing or there is no external force affecting this body to vibrate. Just pull it and leave. The same concept if we have pendulum like this, if we push it to move right and left and so on, the same, we call it free vibration, that you are push and leave it vibrate. But the most important one for our defects here is the forced vibration. Why? Because forced vibration is the vibration come from external source, and this external source is our target now. Because the external source here is the defect itself. Like here, when we talk about here, is we have unbalance. Unbalance making this external source due to this mass. You know what the unbalance? The unbalance mean the geometrical center line is different than the CG or gravity center line, which making this centrifugal force due to rotation of the cylindrical object, and due to this centrifugal force make external force which called the vibration. Okay. Because the forced vibration generating this vibration due to the force come from defect. Like in case of unbalance here, we have different in center line, the geometrical center line, and CG. Due to this difference, the centrifugal force generated producing this force acting on the body or the machine, making this vibration. Okay, here we have the bearing defect problem, and due to this bearing problem, which may come from balls, cage, inner race, outer race, any part of the machine or any part in the bearing could be fail, producing vibration also, making the body vibrating. Pin shaft, cutting belt, looseness, like here, all of this can make this vibration. That's why it's important for me to measure the vibration and make this analysis to figure out what the source of the problem is. Is it come from imbalance, from bearing, from pin shaft, from looseness, from anything? Final one is a damped vibration. The third type of vibration, damped vibration. That you already have vibration, but you add something to damp this vibration. Exactly like in the car. You found that the car wheel here is go over the road, and maybe the road is not flat, and due to this the tire is coming up and down, but this dashboard or damper absorbing this vibration reduce the amplitude, so it's not vibrating all the time, it stop at the certain time, it's damping this amplitude, which is very important actually to control the vibration amplitude. Then we need to represent the vibration in simple harmonic motion this way. If you found here, this movement of the machine can be represented as this time waveform, and we call it sine waveform. We call it time waveform, but in this case, because it's simple harmonic motion, like very simple one, it's represented as sine wave, like this. Due to this simplicity, as you can see here, if we're representing this rotating point, found it makes this complete revolution. Then if you fold up or expand this rotation, you find it represented as a sine wave. Okay, that's why we found that here we can represent this movement by this equation: x equal a sine omega t plus phi. Okay, and of course in the course we talk about all of these details. But how we quantifying, how we measure the value of this wave? By using these three main values. First we call it peak amplitude, and the second one we call it peak to peak, and the third one we call it RMS or root mean square. These are the three values representing these time waveform values. But in this case, if we talk about time waveform, how we can detect exactly what the source of this time waveform, especially if we have many parts in the machine. Like here in this example, we have 1, 2, 3, 4 parts in the machine. Like for example, if we have motor, rotor, the motor is having the motor has rotor, bearing, 2 bearings, not 1 bearing, and the rotor itself, the stator, many things, and then coupled with the machine using coupling, using the pump has bearing, has impeller, many things. Then each part of this producing not only even one waveform, but many waveforms. Like in bearing, we have 4 parts in the one bearing, in each bearing. Then by considering all these parts coming together, you can't make this analysis very easy. That's why we go through fast Fourier transform we having